Hello everyone, I'm Finn, and I'll be talking about work that we've been doing toward a quantum programming language for higher level formal verification. Our main motivation is that we would like to be able to write high-level quantum programs and then reason that they are correct. However, today's quantum programs are often expressed at a low level as circuits, and means for assuring their correctness, like testing and simulation, are difficult and expensive. To address these issues, we designed a programming language that we're calling Quantum 1. Quantum 1 is closer in abstraction to a normal programming language, and it's designed to be more amenable to formal verification. Specifically, all of the definitions that I'll go through have been formalized within the cock-proof system. This language also includes some useful features. It includes both unitary and measuring operations. Classical and quantum data can be used interchangeably, simplifying the type system. Program state is expressed as a superposition of expressions, simplifying the semantics of the language a bit. And then the language is still fairly powerful, allowing not only tagged unions, but superpositions of them and coherent operations that can be done on these superpositions. We've also written a compiler from Quantum 1 to low-level Squire circuits, allowing programs to be run on actual quantum hardware. Next, we can talk about Quantum 1 syntax. This is the formal definition of the syntax. We have x ranging over some infinite set of variables and g ranging over some set of single qubit gates. And then expressions are defined in this way and functions are defined in this way. You'll notice that this is mutually recursive because expressions are defined in terms of functions and functions are defined in terms of expressions. You'll also notice that most of the features of this language are standard in many classical programming languages. For example, there's a unit value, left and right tagged unions, pairs, variables, case analysis for acting on tagged unions, let expressions for destructing pairs, functional abstraction, and function application. You'll also notice that this language includes two fundamentally quantum features, specifically gate application, enacting a single qubit unitary gate, and control statements. The control statement is a lot like the case statement, except it outputs a potentially entangled pair, including both the value controlled on as well as the output. There are also a few notational conventions that we'll use. Specifically, we'll use tagged unions to represent bits, and we'll be able to use let expressions and function application fairly interchangeably. Using these features, a lot of standard classical functions can be implemented as normal. We can here implement a first and second function that output the first or second element of a pair, for example. But then the language also includes some quantum gates, which are the only way to produce superpositions in the language. So for example, you could have a Hadamard in your gate set, and then you could define the plus and minus like this, Hadamard 0 and Hadamard 1. The control statement in this language is an entangling operation, and it can be used to define the CNOT gate here. So the CNOT gate takes in a pair of qubits x, y, and then applies the poly x gate to y, controlled on x being 1. It outputs a pair that contains x as well as the output. Using this language, algorithms like Deutsch's algorithm can be written very simply. Here it is defined on the top line here, where u sub f is a unitary oracle defined in the usual way. So if our hidden function f is the identity function, then u sub f could be the CNOT gate defined on the previous slide. One interesting property of this language is the way that duplicated variables are shared rather than cloned. Many languages distinguish between classical and quantum data, and for quantum data they use linear types to prevent duplication. In Quantum 1, however, duplication is allowed, but it's treated as sharing rather than cloning. So in the last row of this table here, you can see that the variable x is used twice. It's used in a way that would be disallowed by linear types, but in Quantum 1 this is allowed and it produces an entangled pair. Another interesting property of this language is the way that unused variables are discarded, and this can be used for measurement. So for example, we have two functions here that are equivalent, and they can be used to measure a qubit. This first example, it uses the variable x twice, so the variable x is duplicated, but then only one of those duplicates is used and the other one is discarded. So this causes the variable x to be measured. The second example is very similar. It works in a slightly different way. The variable x is still duplicated because it's used in a nonlinear way, and then y is not used. And so one of those two copies is discarded and the variable x is measured. Some of this duplication and discarding may make more sense when we get into the operational semantics of the language, which we'll do next. So a program state in Quantum 1 is a linear combination of expression, discard list pairs. Here, expression is a Quantum 1 language expression, and the discard list is a list of values that have been discarded. We'll get into the reduction semantics next, but if we have a fully reduced program state, then it can be interpreted by taking the partial trace over the discard list, partial trace over the space of values that have been discarded. So these top two examples here, the discard list is empty, so we can interpret them just as pure states. Whereas in this third example, there is information in the discard list that is entangled with the expression. And so in this case, this is the maximally mixed state. In the last example, the expression is not fully reduced, so it's hard to directly interpret as a quantum state. Now we can talk about how program states are actually reduced using our small step operational semantics. Here we're using this squiggle arrow to represent how expressions are reduced to program states. In these first two examples, we're comparing the case statement and the control statement. So in the case statement, you can see that this 1 here is discarded and is added to the discard list. In the control statement, however, this 1 is not discarded. Instead, it's included in the output as part of a pair. The case of function application is similar, but here what matters is whether x is used as a free variable in the expression e. On the left here, x does appear free in e, and so this value v is substituted into e. In the case on the right, x does not appear free in e, and so this value v is added to the discard list. Unitary gate application works essentially as you'd expect. It's just matrix multiplication and nothing is added to the discard list. As an example of the semantics in action, here's a simple coin flip program that measures a plus state. You can see it uses the measurement function as we've defined before and the plus state. And so the first step that happens in the semantics is that the Hadamard gate is applied to the 0 state, splitting the superposition into two branches. Then a function is applied to the 0 state, and another function is applied to the 0 state, but this time the 0 is not used, and so it's added to the discard list. Then the same thing happens in the other branch, leading to the maximally mixed state as expected. So now we've discussed the operational semantics, and we can move on to the typing relation. The types in Quantum 1 are fairly standard, similar to what you'd see in a classical programming language, and functions are first order only. Expression types are represented with the letter T, and they're defined to be unit, or sum types, or product types. And function types are defined in terms of expression types. It's just an expression to an expression. Typing judgments are also of the typical form. We have slightly different notation for typing expressions versus functions. But here, gamma is the same in both of these. It's the standard typing context, a mapping from variables to types, which can be used to type other expressions or functions. Most of Quantum 1's typing judgments are listed here. I won't go through all of them because they're essentially the same as what you would see in a typical classical programming language, with the addition of primitive gates, which have type bit, arrow, bit. One other thing that's typed a little bit differently in Quantum 1 is the control statement. So you can see here we're comparing the typing of the case statement versus the control statement. The case statement acts pretty much like it would in a classical language. You can see it outputs something of type T, which is the same as the type of the branches E0 and E1. But in the control statement, it outputs a pair containing both the input thing that we're controlling on, as well as the output of the branches, which is of type T. The control statement also has some stricter requirements. This is to enforce that there is no controlled discarding of information, no controlled measurement. And so we enforce that the free variables in E0 and E1 are the same. This prevents a variable being used in one branch and discarded in the other. And then we also have this discard-free property that we enforce that both of the branches be discard-free. I won't go through the whole details of how this discard-free relation is defined, but you can look at our paper. It's essentially what you would expect. Whenever a variable is created, it has to be used. We've now discussed the typing relation of this language and can now talk a little bit about compilation. So we have designed a compiler from Quantum 1 to Squire. Squire is a small quantum intermediate representation. It's designed for describing quantum circuits. Our compiler is designed so that discard-free programs compile to unitary circuits, while non-discard-free programs compile to circuits with measurement gates. If we look at the output of our compiler, it becomes clear that there's a lot of room for optimization. So on the top here, we have our coin flip program from before, measures a plus state, and on the bottom is the output of our compiler when given this program. So just taking a quick glance at this circuit, it is correct, but it obviously uses a lot more gates than it needs to. And in particular, it uses a lot more swap gates than it needs to. This is because the compiler has several invariants built in about where the input wires are supposed to be and what wire is supposed to be used for output. And so this means that a lot of swap gates end up being used to move the output to where it needs to be. Now, this is something that Vox could be used to deal with. So Vox is a verified optimizer for quantum circuits. It is designed for Squire programs, and it can be used to optimize programs like this significantly. We've looked a little bit at compilation, but there's still a lot of work to be done in this area, particularly in verification and some additional features to be added to the language. In terms of verification, there are still a lot of properties of the language that still need to be proven and verified. For example, some standard properties from programming languages like type soundness and normalization. There are also some calc tactics that it would be useful to write for manipulating Quantum 1 programs. For example, automatically reducing expressions, substituting in equivalent expressions, and then we could also look into a notion of approximate expression equivalence and use tactics based on robustness for reasoning about these. Additionally, the compiler is not yet verified. We still need to show that the semantics of Quantum 1 programs are equivalent to the semantics of the compiled circuits. In addition, there are some features that could be added to the language to make it more expressive. For example, a way to safely discard qubits that are in a known state. There are plenty of unitary operations that can be described in terms of discarding a qubit known to be reset to the 0 state, but these operations are not discard-free in Quantum 1, and so you would be unable to use them within a control expression. In addition, it would be useful to have a way to convert an operation into a reversible subroutine that can be used as an oracle in another algorithm. This is typically done by taking a circuit like the one above and converting it to a circuit like the one below, uncomputing garbage. The problem is that when this circuit has probabilistic or quantum behavior, then the garbage is not fully uncomputed, and so defining the semantics of a language that has such a construct is a little bit tricky. To conclude, we're still fairly far away from our end goal, which is higher-level formal verification. The ideal workflow that we'd like to see is to write an algorithm in an intuitive high-level language, then verify the correctness of the algorithm, and then compile the program using a verified compiler. We've written a language that could be used for this purpose, though it's debatable whether it's as intuitive or expressive as it could be. And we've also written a compiler for this language, but there is still a lot left to verify. We hope that this language could be a useful step toward our end goal, and that it presents some features that could be useful in the future.